Hey guys, welcome back. Today we are going to talk about acids and bases, and specifically we're going to talk about a new definition of acids and bases called the Bronsted-Lowry definition. So let's get to it. So in the Bronsted-Lowry definition of acids and bases, there is one thing that stays the same. Acids are still the guys that are giving H plus ions. So anything with an H plus ion is still the acid. The difference is that the base is the thing that accepts the proton. So it doesn't have to be hydroxide anymore. It just has to be something that takes that H plus ion. So for example, this makes sense now if you go to your reference table. When you look at the table of common acids, table K, you see all of the acids still start with the proton or the H plus ion. However, all of the bases don't have hydroxide in it. So sodium hydroxide has hydroxide, potassium hydroxide has hydroxide, calcium hydroxide has hydroxide, but ammonia does not have hydroxide, and yet ammonia is a common base. So bases don't need hydroxide to be a base. Bases just need to be able to accept H plus ions, the H from one of these guys, according to Bronsted-Lowry. So according to Arrhenius, our original definition, these three are Arrhenius bases. I will write that. So this is Arrhenius. And this guy is considered Bronsted. Bronsted-Lowry. Okay, so we have 3 Arrhenius bases and 1 Bronsted-Lowry base on our table of common bases. So again, a Bronsted-Lowry acid is anything that donates a proton. This is similar to an Arrhenius acid in that it makes a proton when dissolved in water. And the difference is the base. The Bronsted-Lowry base is not defined as being hydroxide. It is defined as just accepting the proton from the acid. So here's an example. We have water reacting with ammonia, which again I just defined ammonia from your reference table as being a Bronsted-Lowry base. And they react to form NH4+ and hydroxide. So what's going to happen, normally you might say water is not an acid or a base, but because you have a base here, the water is going to act as an acid. I know, weird. But the reason why it acts as an acid is because it has a hydrogen, and ammonia, which is the base, wants that hydrogen. So the water is going to give up that hydrogen. So it's considered the acid, and the ammonia is the base. So this hydrogen is going to go whoop right onto the base, and that's why it forms NH4+. It literally stole an H+. And then the product, once water loses an H, it's just a single H, so it's OH. And it lost an H+, so it's OH-. So, again, ammonia is considered a base just because it steals an H+ from the acid. And now our products, you can define this ammonium as the conjugate acid. So what that means is because ammonia was the base and it stole a proton, it now is more acidic as a product because it has that extra H+. So it kind of like do-si-dos and switches, because now the ammonia turned into ammonium is the conjugate acid, and water, which was the acid, is now the base. It's the conjugate base because it's lost its acidic proton. So now it's just OH minus, and this is hydroxide, so it's a base. And this has the H plus, so it makes sense it's the acid. So let's look at, here's the same example, but here's like a better picture of it. So again, you start off with water and your ammonia, and ammonia, NH3, based on your reference table, it tells you that it's a base, and it steals the H plus, just the hydrogen with no electrons, so it's called a proton. So it steals the H goes right onto the ammonia, and it forms NH4 plus. And so the base, whoever's the base is always going to turn into the conjugate acid in the products, and whoever is the acid will always turn into the conjugate base. So kind of it switches. Alright, let's look at some further examples. So we already went over the top one. We have our acid and base, and the proton from the water goes on to the base and forms NH4 plus, which is the acid, conjugate acid, and OH minus, which is the conjugate base. Here's another example, and you might say, I wonder who the acid and who the base is. You might assume because water was the acid in the last example that water is the acid again. Do not jump to conclusions too quickly. This is chemistry. If you take a second and check your table K for common acids on your reference table, you will see that HNO3 is nitric acid. So because this is the acid, it forces water, the other reactant, to be the base. So in this example, HNO3, like we said before, is the acid, and water is thereby forced to be the base. So can you figure out who the conjugate acid and who the conjugate base is? If water starts out as the base, then in the products, it has to be the conjugate acid. And if HNO3, nitric acid, starts off as an acid, in the products, it has to be a conjugate base. It always flips. So here, because again, acid is defined as giving up the proton, the acid is going to give its H plus over to water, forming H3O plus, and the base is going to be left without the H plus, so it's just NO3 minus. Okay, and then, the conjugate acid and the conjugate base, they could always react, and then the H would switch back onto the base, but this is considered to be a weaker acid and a weaker base, so the forward reaction is going to happen first. You don't have to worry about which one's going to happen more. Alright, so I have some examples of acids. Notice again how they all start with the H. And I want you to try to come up with their conjugate base. So what are they going to look like after they've lost their H plus? So for the first one, this is hydrofluoric acid. If you lose the H plus, then you are left with fluoride, F minus. You might say, Miss West, how did we know that HF was the acid and not the base? Well, generally, if it has the H first, and it's not water, which is neutral but could go either way as acting as an acid or a base at times, it's going to be the acid. The other way you can know that hydrofluoric acid is the acid is by checking with your reference table. So on table K, you'll see there's a whole bunch of common acids listed, and while HF is not listed, HCl is pretty much the same thing. I mean, if you go down to your periodic table, you'll see that fluorine and chlorine are in the same group. So hydrofluoric acid is very similar to hydrochloric acid. So as long as an element is in the same group, it's kind of interchangeable. And that's why your reference table for the common acids, they don't list everything because there'd be too many acids. But you can kind of figure out the other acids based on the ones that they have listed. So the next, we have an acid listed here, and if you weren't sure if it's an acid, again, note how there's an H right in front. So that's one way to indicate that this is an acid. The other way is to check your reference table, so it's H3PO4, and table K tells us that it is phosphoric acid. So we know this is an acid, and so what do you think its conjugate base will look like if it loses an H+? Its conjugate base will be H2PO4 because it has lost one H, so that's why it went from H3 to H2, and it lost a positive charge. It was neutral before, so if it's neutral and it loses a positive charge, then it's going to have a negative charge. Alright, last one, let's try H3O+, which is also noted as hydronium. This is not going to be on your reference table, it's just another way to indicate an acid. So you should get used to seeing H3O+, hydronium. So its conjugate base, what do you think that will look like? So when it loses an H+, it will literally have one less H, so again going from 3 to 2, and it lost a plus, so now it goes from positive to neutral. Notice how this went from neutral to negative, this went positive to neutral. So whenever you're going from the acid to its conjugate base, you are going down in number by 1, assuming you've only lost one proton. Okay, now let's look at some bases and see if we can figure out the conjugate acid, so what it will form once it's reacted with an acid. So here we have Br-. What will it look like when it's gained an H+? So it will be HBr, hydrobromic acid. So adding a plus to the negative will bring you to neutral, and adding an H to it is just going to put an H out in front. What about this guy if we add an H to this base? So again, this is starting off as negative. So if you add an H+, it's going to go from negative to neutral, and you're going to gain an H. So our product will be sulfuric acid, H2SO4. Alright, for the last one, we have CO3 2-. If you gain an H+, it's just 1+, so +1. We're going to go from 2- to just 1-. You only go up by 1 point. And you're going to have an H in front. So it will be HCO3-. So because bases are gaining a proton, they're always going to go up 1 in charge. So from, if it's negative, it's going to go to neutral, like these two guys. And if it's more negative, it will go to less negative. If it was neutral, it would go to positive. There's no examples of neutral, but you could have a neutral, like water could act as a base. You could have neutral water, and then it would go to positive H3O+. So, and notice how all of the bases, they just gained an H also, a single H. It went from no H to 1H, 1H to 2 H's, no H's to 1H. So there, it's just kind of like a blob, and you're adding an H+ to that blob. Okay, so that is all the definitions that you are going to learn for acids and bases. So we have the Arrhenius acid-base definition, where the acid is defined as being a proton, H+, and the base is defined as being hydroxide, OH-. And then you learned the Bronsted-Lowry definition today, which is the acid is H+, and the base just accepts that H+.